let's learn about matrices. So what is a, and what do I mean when I say matrices? Well, matrices is just the plural for matrix, which is probably a word you're familiar with more because of Hollywood than because of mathematics. So what is a matrix? Well, it's actually a pretty simple idea. It's just a table of numbers. That's all a matrix is. So let me draw a matrix for you. I don't like that toothpaste colored blue, so let me use another color. So this is an example of a matrix. If I said, I don't know, I'm going to pick some random numbers out. 5, 1, 2, 3, 0, -5. That is a matrix. And all it is a table of numbers. And oftentimes, if you wanted to have a variable for a matrix, you use a capital letter. So, you could use a capital A. And sometimes in some books they make it extra bold, so like a bold A would be a matrix. And just a little bit of notation. So they would call this matrix, or we would call this matrix, just by convention. You would call this a 2 by 3 matrix. And sometimes they actually write it 2 by 3 below the bold letter they use to represent the matrix. And what is 2 and what is 3? Well, 2 is the number of rows, right? We have 1 row, 2 row, right? This is a row, this is a row. And we have 3 columns, 1, 2, 3. So that's why it's called a 2 by 3 matrix. So when you say, if I said that B, I'll do it extra bold. If B is a 5 by 2 matrix, that means that B would have, I'll just type in numbers 0, -5, 10. And it has so it has 5 rows, it has 2 columns, so it'll have another column here. So let's see, -10, 3. I'm just putting in random numbers here. 7, 2, pi. That is a 5 by 2 matrix. So I think you'd have kind of a convention that all a matrix is a table of numbers. You can represent it when you're doing it in variable form. You represent it as a bold-faced capital letters. Sometimes you'd write a 2 by 3 there. And you can actually reference the terms of the matrix. So in this example, in the top example where we have matrix A, if someone wanted to reference, let's say, this element of the matrix. So what is that? That is in the second row. It's in row 2. And it's in column 2, right? This is column 1, this is column 2. This is row 1, row 2. So it's in the second row, second column. So sometimes people will write that A, and they'll write, 2, 2 is equal to 0. Or they might write, sometimes they'll write a lowercase A, 2, 2 is equal to 0. And just as what is A? And these are just the same thing. I'm just doing this to expose you to the notation, because a lot of this really is just notation. So what is A 1, 3? Well, that means we're in the first row and the third column. First row, 1, 2, 3. It's this value right here. So that equals 2. So this is just all the notation of, well, what a matrix is. It's a table of numbers. It can be represented this way. We can represent its different elements that way. So you might be asking, Sal, well, that's nice, a table of numbers with fancy words and fancy notations, but what is it good for? And that's the interesting point. A matrix is just a data representation. It's just a way of writing down data. I mean, that's all it is. It's a table of numbers, but it can be used to represent a whole set of phenomena. And if you're doing this in your Algebra 1 or your Algebra 2 class, you're probably using it to represent linear equations. But we'll learn later that and I'll do a whole set of videos on applying matrices to a whole bunch of different things. But it can represent. It's very powerful if you're doing computer graphics. A matrix, the elements can represent pixels on your screen. They can represent points in coordinate space. They can represent, who knows? There's tons of things that they can represent. But the important thing to realize is a matrix it's not a natural phenomenon. It's not like a lot of the mathematical concepts we've been looking at. It's a way to represent a mathematical concept, or a way of representing values, but you kind of have to define what it's representing. But let's put that on the back burner a little bit in terms of what it actually represents. And then, oh, my wife is here. She's looking for our filing cabinet. Wait, But anyway, back to what I was doing. So let's put on the back burner what a matrix is actually representing, and let's learn the convention, because I think at least initially that tends to be the hardest part. How do you add matrices? How do you multiply matrices? How do you invert a matrices? How do you find the determinant of a matrix? I know that all of those words might sound unfamiliar unless you've already been confused by them in your algebra class. So I'm going to teach you all of those things first, which are all just really human defined conventions, and then later on I'll make a whole bunch of videos on the intuition behind them and what they actually represent. So let's get started. So let's say I wanted to add these two matrices. Let's say the first one, and let me switch colors. So let's say I'll do relatively small ones, just not to waste space. Say I have the matrix 3, -1, I don't know, 2, 0. I don't know, let's call that A, capital A. And let's say matrix B, and I'm just making up numbers. Matrix B is equal to -7, 2, 3, 5. So my question to you is, what is A, so I'm doing it bold like they do in the textbooks, plus matrix B. So I'm adding two matrices. And once again, this is just human convention. Someone defined how matrices add. They could have defined it some other way, but they said we're going to make matrices add the way I'm about to show you because it's useful for a whole set of phenomena. So when you add two matrices, you essentially just add the corresponding elements. So how does that work? Well, you add the element that's in row 1, column 1 to the element that's in row 1, column 1, right? So it's 3 plus -7. So 3 plus -7. That'll be the 1, 1 element. Then the row 1, column 2 element will be -1 plus 2. -1 plus 2. Let me put parentheses around them so you know these are separate elements. And you could guess how this keeps going. This element will be 2 plus 3. So 2 plus 3. And this element, this last element, will be 0 plus 5. 0 plus 5. So that equals what? 3 plus -7, that is -4. -1 plus 2, that's 1. 2 plus 3 is 5. And 0 plus 5 is 5. So there we have it. That is how we humans have defined the addition of two matrices. And by this definition, you can imagine that this is going to be the same thing as B plus A. Right? And remember, this is something we have to think about because we're not adding numbers anymore. You know that 1 plus 2 is the same thing as 2 plus 1, or any two normal numbers. Doesn't matter what order you add them in. But matrices, it's not completely obvious. But when you define it in this way, it doesn't matter if we do A plus B or B plus A. Right? If we did B plus A, this would just say -7 plus 3. This would say 2 plus -1. But it would come out to the same values. That is matrix addition. And you can imagine matrix subtraction. It's essentially the same thing. Well, actually, let me show you. What would be A minus B? A minus B. A minus B. Well, you could also view, and this is capital B, it's a matrix. That's why I'm making it extra bold. Well, that's the same thing as A plus -1 times B. And what's B? Well, B is -7, 2, 3, 5. And when you multiply a scalar, when you just multiply a number times a matrix, you just multiply that number times every one of its elements. So that equals A, matrix A, plus the matrix. We just multiply this -1 times every element in here. So 7, -2, -3, and 5. And then we could do what we did up there, and we know what A is. So this would equal, let's see, A is up here. So 3 plus 7 is 10. -1 plus -2 is -3. 2 plus -3 is -1. And 0 plus 5 is 5. And you didn't have to go through this exercise right here. You could have literally just subtracted these elements from these elements and you would have gotten the same value. I did this because I wanted to show you also that multiplying a scalar times, or just a value or a number times a matrix, is just multiplying that number times all of the elements of the matrix. And so what by this definition of matrix addition, what do we know? Well, we know that both matrices have to be the same size by this definition, the way we're adding. So, for example, you could add these two matrices. You could add, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9 to this matrix, to, I don't know, -10, -100, -1000. I'm making up numbers. 1, 0, 0, 1, 0, 1. You can add these two matrices, right? Because they have the same number of rows and the same number of columns. So, for example, if you were to add them, the first term up here would be 1 plus -10, so it would be -9. 2 plus -100, -98. I think you get the point. You would have exactly 9 elements, and you would have 3 rows and 3 columns. But you could not add these two matrices. You could not add. Let me do it in a different color, just so it's different. You could not add, in this blue, you could not add this matrix, -3, 2, to the matrix, I don't know, 9, 7. And why can you not add them? Well, they don't have corresponding elements to add up. This is a 1 row by 2 column. This is 1 by 2, and this is 2 by 1. So they don't have the same dimensions, so we can't add or subtract these matrices. And just as a side note, when one of its dimensions is 1, so for example, here you have 1 row and multiple columns. This is actually called a row vector. A vector is essentially a one-dimensional matrix where one of the dimensions is 1. So this is a row vector, and similarly, this is a column vector. And that's just a little extra terminology that you should know. If you take linear algebra and calculus, your professor might use those terms, and it's good to be familiar with it. But anyway, I'm pushing 11 minutes, so I will continue this in the next video. See you soon.